there are cracks. Let's write a paper about that. What we need to do is we need to actually quantify those cracks. And you would be pretty shocked by the number of papers that I read where people were counting cracks by hand, which seems insane, and I almost did go insane for the first hour that I attempted to do that. So I said, okay, I'm an engineer, we can automate this process. And the way we decided to automate it was, if you look at this picture, it's really just a signal. It's a two-dimensional signal with variances in intensity. So large intensities represent spots that are higher, and low intensities, so darker parts, are spots that are lower. And cracks are really just variations from a high intensity to a low intensity back to a high intensity. So if we can figure out where those variations occur, we can find the cracks. And so that was the first thing we tried. But unfortunately, signal noise, which you can't really see in these pictures, is also characterized by fluctuations in signal intensity. And even just some of the shadowing that occurs. I think this picture has some good shadowing on it. That's also characterized by high intensity, low intensity, and then high intensity. So then it became a question of, well, how do we distinguish the actual surface variation, or the actual intensity variations we want to see, and call cracks? And to do that, we basically just took a Fourier transform of the whole image in 2 dimensions, and then that allowed us to look at things in terms of intensity variation frequency. And so high variation frequencies like signal noise that might exist all around, we could eliminate. And then low intensity variations that are represented by like shadowing or changes between boron nitride and silica boundaries, we could also eliminate, and that left us with the cracks. So we used that method to actually determine where our cracks were at. And then, oops, I'm going the wrong direction. And then with that information, we decided to quantify how cracked this area was by using the cracked area ratio. So all we did was we just said, okay, the total cracked area the computer finds, divide that by the total image area, and that's how we're going to quantify our cracking. So here are the results from that image that you saw there. And what we see is a nice curve here that appears to be asymptoting somewhere around 12, 13, 14%. And we see that the very first cycle, as expected, creates the vast majority of the cracks. Then after that, like I said, we begin to asymptote. So that's nice. We were able to quantify cracks. We were able to show that thermal cycling was enough to create these cracks. That's all nice and good. But what we're really interested in is, how do these cracks actually impact the plasma erosion process? And so that's the next part of this talk. So we set up an experiment to try to figure that out. So we ground and polished another borosil sample down to the same initial RMS surface roughness of about 0.2 microns. And then we simultaneously exposed the control and cycled samples to argon plasma in GTRI's ion-assisted deposition chamber for about 10 hours. And that 10 hours of exposure was enough to create an erosion depth on the order of 10 to 12 microns. And then we took surface telemetry on both the cycled and non-cycled samples, so the control sample, before and after exposure, to determine what the impact of these microcracks was on the plasma erosion process. And so the first thing we did was we took advantage of the fact that we can take these electron microscope images that nobody else can, and we tried to see if there were any qualitative differences. And we did not see any qualitative differences. What we saw was the same micro-ridge development between the two. We saw material separation, which is likely cracks caused by the thermal load of the plasma itself. And we saw striations, which look a lot like what you see at the bottom of a riverbed due to water erosion. So we see these identical features, and we're like, oh great, so the cracks don't seem to matter. But there's more to the story. If I can ever seem to, okay. To try to quantify how the cracks affected plasma erosion, we used contact profilometry to take height profiles of the surfaces before and after plasma erosion. And the first thing that lets us easily quantify is like, well, how did the RMS roughness change before exposure and then after exposure? And interestingly, we found that the control sample had a higher higher relative increase in RMS roughness due to plasma exposure. And so we thought, okay, that's kind of interesting, but we need to do more tests to see if that's significant. But maybe preliminarily we can conclude that the cracks are somehow dampening roughness growth. Okay, I don't really understand why that would be happening or what that means. To further try to quantify that, we use something called an amplification function, which is literally just a comparison of the Fourier transform of the height profile after plasma erosion to the Fourier transform of the height profile before plasma erosion. And that's plotted over here. And this is very interesting because this lets us actually see how features are amplified as a function of spatial frequency. And this is where we try to get some more interesting information, because you can see for these lower spatial frequencies, which correspond to much larger feature dimensions, that there's similar amplification between the two samples. But over here on the other end of the graph, where we're running into the high spatial frequencies, so the very small surface features, we see that the control is experiencing much larger amplification. So what that appears to mean is that the cracks are for some reason dampening growth of small feature amplification specifically. So maybe this trend over here is real, and it's happening at these small scale features. So that's just the summary of those results. So before we try to get into why that's happening, I'm going to do a brief aside on sputtering, because I doubt many of you had much experience with plasma erosion before. So in our field, we typically consider plasma erosion on an atomic scale. So we say the ions collide with the wall, and they basically impart enough energy to eject wall atoms in a process that we call sputtering. And boron nitride has a sputtering yield about half that of silica, so you would expect that after Hall thrusters run for a long time, you're going to have a smaller relative fraction of boron nitride, you expect the relative fraction of boron nitride to silica to increase because the boron nitride has this lower sputtering yield, so it should be less likely to be ejected. Okay, cool. Unfortunately, past studies in our field have found the opposite trend, and actually boron nitride seems to somehow be sputtering faster, potentially, than the silica. So that's really weird. And the question is, what might our results have to say about this perplexing trend? So, a crack can be thought of as a structural instability. And if you have a structural instability, you open the door to the possibility of material ejection happening on a granular scale as opposed to on an atomic scale. So those boron nitride silica grains that we saw could be potentially being lifted off of the surface in chunks as opposed to at the atomic level. And it's interesting because we found cracks predominantly in the boron nitride grains, which means that the boron nitride might actually be more susceptible to granular ejection. Additionally, the boron nitride is anisotropic, whereas the silica is isotropic. So the boron nitride is a lot rougher than the silica. So what that might mean is that if you were preferentially ejecting boron nitride at a granular scale, you could end up seeing relative dampening of small-scale feature growth, because the boron nitride would be gone, you'd be left with the smooth silica. And that's actually what we found. We found in the cracked sample, we found this dampening of small-scale feature growth on scales that were smaller than the boron nitride and silica grain sizes. So we think, hey, maybe that is what is, maybe these microcracks are existing in all Hall thrusters, and that's potentially leading to this granular ejection that occurs. And that could be causing the boron nitride to actually be essentially removed from the thruster wall faster than the silica. So obviously, for some ongoing work that we're doing right now, we want to quantify this with a much larger set of samples and images and establish some trends and some measurement uncertainties to try to confirm the results we found from this pretty small scale experiment. And in addition, we want to see if, by using X-ray photoelectron spectroscopy, whether or not the chemical makeup of the borosil surface is changing in the way that I just told you that it was. And that would allow us to quantify this a little bit better than trying to simply use profilometry to determine whether or not those microcracks are actually causing the boron nitride to be ejected more than the silica. And finally, just purely because we were able to get these pictures and nobody else could, Princeton Plasma Physics Lab got really excited and they said, hey, we want to look into how these induced cracks might be affecting secondary electron emission, which would help explain a feature in our field called the Hall thruster bake-in time, which I don't believe I have time to discuss right now. So I will end the presentation right here and say thank you, and I'll take any questions. Yes?
So the crack image processing technique that you guys developed, are you using, so past actually quantifying that cracking did occur as you thermal cycled. Are you using that process for other investigations in this work?
Like the ongoing investigations?
So yeah, so are you still taking these images and using this image processing to?
Yes, yeah,
Okay.
very much so.
Then did you guys have any method for error quantization for those images? Because if you could go back to those images with the you showed the red.
Oh yeah,
And the
yeah.
cracking?
This is even from an older version of the code.
Okay.
Yeah. I know what you're talking about. Yeah.
Yeah.
So that's not perfect, right?
Okay. Yeah.
So the question is, how are we going to quantify that? And we haven't decided yet. We've thought about maybe if you quantify cracking over a very large number of images, maybe then you can say, okay, there's some sort of standard deviation associated with this. Maybe that would be a decent. It's not really an error measurement, but it gives you an idea of variance. And another idea is to make somebody actually sit there, probably me, and try to like get a really accurate, like, okay, this is what I believe the cracks are, and compare that to what the code finds as well. Yeah. So that's something that we're still thinking about. That's a good question. Yes.
Is this profilometry based on the images, or is this based on like an AFM or something?
Sorry, so this is a contact profilometer that we actually scanned across the actual surfaces, and we took like 50 line scans across the middle and averaged it.
Is that an AFM?
No, so AFMs are super sensitive, but they can only handle, I think the AFM we have here at Georgia Tech can only handle something like 5 microns of height variation, and we're taking really long line scans on the order of like 50 millimeters. So if you do that, then what happens is that you just have basic surface tilt that will cause the AFM to break, essentially, because you'll break that 5 micron.
And then if I may, was this
Sure.
multiple samples that showed these kind of average trends, or was this 2 unique samples that gave you, like, is it possible that this is just one example of a cycle and one controlled?
Yeah, exactly. So that's why we want to do this a lot more.
Okay.
Yeah, I agree with you. I saw those results and I'm still a little bit skeptical myself.
Okay.
But the fact that it kind of fits into some of the trends that other people have found in other fields makes me believe it a little bit more. But certainly before I make any real conclusions, I'll be doing this a lot more.
Okay.
Yes. Agreed.
Thanks.
Yes.
So coming back to your image processing, do you always get closed structures, or do you get like incomplete?
Yeah. It's pretty good at finding closed structures unless those structures intersect the boundary of the image. And then we run into a few problems. And so we have some other filters that we actually put in there to try to mitigate that a little bit, but that's actually still something that we're working on a
So
little
if
bit.
you don't get a closed structure, do you just leave it, or do you assume a thickness to it or something like that?
That doesn't happen super often. And so it's the kind of thing that like I said, we're still trying to kind of deal with it a little bit, but it tends to be more in the noise of the image. The other thing that we're doing in our next work is, rather than looking for the same image every time, we're taking a large chunk of images that comprise a large like area. So if you stitch them together, you'd have one big image. In which case, you could really say, okay, I really don't care about some of the minor results I get on the edges there. So, but that's part of how we're thinking about trying to mitigate that effect. Yes.
This may be a super basic question,
Yeah.
but why do we use borosil for this? Like, isn't there a dielectric that's high temperature that doesn't have these 2 materials that have 50 times different thermal expansion?
Yeah, so our field, the longer I've been in our field, the more I realize that a lot of what we do is because some Russians did it like 30 years ago and worked pretty well. So that's a great question. There's probably a lot of room for material science to be applied here to drastically improve this. But it's the kind of thing where people didn't even realize this was a problem. I mean, it was in 2014 someone said, hey, look, there are microcracks. I wonder why there are microcracks. Oh shoot, there's these huge differences in CTEs. So, yeah. But I will say boron nitride, and sometimes some testers do just use pure boron nitride as well. So, yes.
Do you try any other standard image processing tools like gaming type segmentation or anything like that?
No, we're pretty new to image processing, so we're not aware. I would be happy to talk with you later about some better image processing tools potentially. So we kind of developed it from the ground up. Yes.
Do you apply any type of medicinal
Yeah, we do, because if you don't, you end up with a really interesting ringing effect in your calculation. So we actually apply a second order Butterworth filter to the Fourier transform. Yeah, because if you do a hard cutoff numerically, that's a horrible idea, which we discovered the first time we tried it. Yeah.
Questions? Okay, let's thank our speaker.
Si, do you have closing comments?
Yes, sir, I do.
Okay.
So, before we disperse, I would like to thank Professors Ranjan, Lewin, and Dakota for supporting us for this effort. Thank you for our speakers for your time and effort today. And thank you to the volunteers that have graciously lent their time to help support all of the background work that we have going on for this event, downstairs setup, as well as all the setup inside this room. Special thanks to Dan for coordinating this entire event. A round of applause to that. And the challenging questions that he asked.
Next year he's gonna do the audiovisual stuff.
Yeah,
Can I say something too?
sure.
So I guess, does everybody know what week it is this week?
Graduates.
Grad Student Appreciation Week. So I think, the faculty, I think we should also give a big thank you to all the students, because I think if I think about our lab, what I think differentiates is we work at a very high level, so it's an internationally famous place where we do cutting edge work, but it's also a great place to work where people help each other and work together and support each other, and I love my job. The days have flown by. I've been here at Georgia Tech for 24 years now, and it's because of the great people we get to work with. So it's a big thank you to all the graduate students.
Last but not least, thank you, Dr. Zinn, for joining us again, and hopefully we'll see you at the 4th annual.
The 20th.
Thank you, everyone, for coming, and we will see you at Orange.
And if the speakers that are still here would please come to the banner for a little group picture. And yeah, if you want to continue the conversation, you can